The mission of the Sensor Technology Research Center is to develop novel sensing technologies that can help improve our quality of life. The center is composed of 5 research groups that cover the fundamentals of sensor technologies, looking mostly at electric and magnetic sensors. We also look at wearable sensor technologies, allowing for on-body sensing and understanding of human activities and the context in which these activities occur. The Flexible Electronics group is looking at electronics on plastic substrate that can be integrated into clothing or that can be wrapped around everyday objects. Of course, with a wide range of sensors that we have in our surroundings, we need to interconnect them, and this is the responsibility of the communications group that is addressing emerging challenges coming from new applications and developing novel communication techniques. Finally, the Semiconductor Material and Device group is looking at semiconductors that are other than silicon and develops sensors and detectors that are suitable for extreme environments. The composition of our center allows us to address all the challenges in sensor design, so we can invent, create, develop new sensors, prototype them, characterize them, produce them in small quantities, but also license the technology to third parties. Also, we have all the expertise required to analyze new applications and develop new applications built around sensor technologies. So on behalf of my colleagues, I am going to introduce you the activities of the different groups. But before I do that, I would like to make sure that we all understand what is a sensor. So a sensor is a device that is converting a physical phenomena into an electric signal. For example, a microphone is a sensor. The microphone is responsive to sound, here coming from this loudspeaker. Sound is essentially a pressure wave that is propagating through the air and that is changing over time. Therefore, the microphone is sensitive to this pressure wave and creates an electric signal corresponding to it. This electric signal can then be stored on a computer or can be used after further processing for different applications. Sensors are everywhere in our life. They're really the foundation of our digital life. We try our very best to make sensors as small as possible so that we do not see them in our surroundings. But if we take an example, for example, a car would have about 100 sensors nowadays. Many of these sensors are used for engine and fuel management. And actually today, it would not be possible to create a car that passes the very stringent emission limits without using sensors. But you have also many sensors used in a car for safety reasons. For example, the distance sensors that you find useful when you're parking, or cameras looking on the front for the detection of obstacles, as well as cameras looking at the driver itself to detect if he's about to fall asleep and trigger an anti-sleep alarm. It is predicted that by 2020, there will be about 200 sensors in a car, many of them used also for entertainment and comfort purposes. We have also sensors in our homes to control our heating, to awareness of intruders, or to detect fires. Any industrial process that is automated also requires sensors. And finally, there is a device that all of us are familiar with, which is the mobile phone. The mobile phone comprises a very large number of sensors, and we're going to look at a couple of these sensors more closely based on this example. So we already mentioned the acoustic sensors. So microphones are used to pick up sound during a conversation with your partner. And of course, you can have more than one microphone in a phone to increase the call quality. But we have many other sensors in a phone. For example, sensors measuring electric phenomena. For example, here we can use an electric sensor to measure the current that is flowing from the battery as a way to indicate how long the phone will operate on a battery charge. Sensors can also measure magnetic phenomena. In the case of a phone, that could be the compass that is used to indicate the north and that you can use in your map or navigation application. We have also optical sensors that are measuring the ambient light and that are often used to control the brightness and the contrast of the screen. This is very convenient if you go outdoors or indoors to adapt the brightness so that you have always the ideal visibility. Cameras are also a form of optic sensors. You have also thermal sensors, typically to indicate the ambient temperature to the user, but also to monitor the internal temperature of some of the components of the phone, typically the processor. So if you are playing very long games that are very demanding on the processor, this kind of temperature sensor can be used to throttle the processor to avoid reaching critical temperatures. We have also mechanical sensors in a phone, typically an acceleration sensor that is used to measure the orientation of the phone. This is the kind of sensor that is used to indicate or to change the orientation of the screen when you rotate your phone sideways. Some phones have also physiological sensors to measure heart rate, and many research groups, including ours, are continuously looking for new sensor modalities that we could include in phones or in other kind of devices or in these industrial systems. A few of the sensors that do not exist currently in mobile phones are chemical sensors and biological sensors. Those are mostly used in chemical plants or for life sciences. But it is very possible that in a couple of years, additional sensors will find their way in mobile phones. In some cases, we cannot measure directly the phenomena that is of interest to us, and therefore we need some kind of creativity in the design of a sensor. Typically what we do is measure something which is indirectly correlated to the phenomena of interest. And I will take an example, which is the force sensing resistor. This is a device that can be used to measure the pressure that is applied on a foil. If this foil is placed on a surface, we can obtain a touch-sensitive surface. If it is placed on a screen, we can obtain a touch screen. One common technology, but which is also a low-cost technology, consists in using two conducting plates and in between having a matrix which is made of an inert, non-conducting material. And within this matrix, we can have a number of conducting particles that are floating inside. And as we apply a pressure on the top layer of the plate, the conducting particles will move closer to each other. They will eventually touch each other, and they will establish a conducting path between the top plate and the bottom plate. Now, if we apply a voltage source to the system, we can measure the current that is flowing from the top plate to the bottom plate, and we can see that the current is proportional to the pressure which is applied to the surface. Therefore, instead of directly measuring the pressure, we measure a current, but we know how to calibrate the sensor to obtain the pressure. So there are many characteristics that are important in defining the choice of a sensor. For example, we can look at the measurement performance. Often we're interested in having very high measurement performance, but of course this comes at a cost. When the cost factor is dominant, for example, when we build a phone, we tend to select sensors that are a little bit cheaper. These sensors are sufficiently good to satisfy the consumer requirements, but maybe not as performant as a state-of-the-art system. For example, the heart rate sensor that you would find in a phone is good enough to provide you an indication of your heart rate, but it is not as good as what you would find in a hospital. There are environmental factors to take into account as well. For example, the suitability of the sensor for extreme environments, different temperature ranges that it can withstand. And we have also, more important, recently, human factors to take into account. For example, with wearable sensors or mobile devices, we need to select sensor technologies that have the right form factor, that have the right energy usage, that use the right material to be human-friendly. So these different considerations guide the research of our center, and some of our groups are looking at creating systems that are better at measuring a physical phenomena. Other groups are looking at decreasing the cost of a sensor, making sensor more robust to harsh environments, or making sensors more human-friendly for on-body usage. So the first group in our center is looking at the fundamentals of sensor technologies. It looks at electric sensors and magnetic sensors, focusing mostly on low noise analog sensor design. And one of the flagship sensors that has been developed in this group is the electrical potential sensor. So it is a sensor that is measuring electrical potential, and it is a byproduct or a spin-off of fundamental physics research in the 1990s. So this sensor acts as a perfect voltmeter. This means that it has a very, very high input impedance, virtually infinite input impedance. This essentially means that there is no contact between the sample and the electrode. The electrode can be coated with an inert material like glass or like a plastic, and there is no resistive contact between electrode and sample. So this sensor can be used to measure without contact charges, potential, but also electric field. When it was introduced, it received a wide range of prices, as you can see here. That was in 2011. And now this technology is licensed to a company here in the UK, which is producing this sensor on an industrial scale, and you can actually buy this sensor from this company directly. So let's look at what this kind of sensor technology can do for a biomedical application that is commonly used, which is measurement of electrocardiogram. So electrocardiography consists in measuring the heart activity. That gives this very, very characteristic waveform that can be used to identify heart conditions. The state of the art to measure ECG has been to use resistive electrodes. Resistive electrodes require a resistive contact, direct skin contact to with the skin, and usually there is a gel that is applied between the electrode and the skin to improve this conductivity. Now the state of the art in medical studies consists in doing longer and longer recordings in everyday life. We're interested in looking at ECG during 1 day, 2 days, 1 week, as a way to understand the trends, for example, after drug intake, after surgery, or after various forms of rehabilitation or fitness exercises. The problem with resistive electrodes is that they lead to skin irritation. So we cannot place the electrode on the same location in the body day after day. In some extreme case, they can also lead to allergies. So they are not very well suited for this kind of long-term recordings. We can actually substitute these resistive electrodes by this electric potential sensor that has been developed in our center. This is one of the prototypes that we have with 2 electrodes that are fully insulated, encapsulated into an inert material, and that can be used to measure the heart rate. So here we have no risk of skin irritation, no risk of allergies, so this can be used for very, very long time recording. In addition, because we do not need a direct skin contact, we can also measure the heart rate through the clothing, for example, by placing the electrodes at 2 different locations on the body through a shirt. That's actually very interesting because it opens new possibilities for measurements in a very unobtrusive manner. For example, we can include these sensors in a chair or in a couch, and whenever the person is sitting down on the chair, the system would be able to pick up the heart rate. So that allows us to do very convenient measurement of the heart rate without bothering the user, which is very well suited for long-term monitoring, for telerehabilitation application, and for telehealth applications. As is often the case in research, once we have developed a new sensor technology, we are interested in looking at what kind of other problem domains it can be used. And besides ECG, we have shown that you can use EPS to measure the brain activity. This is called electroencephalography. In this case, the sensor would be placed in a brain cap on the head. We can also use the sensor to measure the movement of the eyes. This is called electrooculography. And the sensor in this case will be placed on the surrounding of the eye or on the glass frames. So we can use that to measure lateral movement of the eye, but also vertical movement of the eye, and the eye blinks. Finally, we can also use this electrode to measure surface electromyography. which is the muscle tension or the muscle clenching, which is very commonly used for rehabilitation and sports application. So in all these examples of physiological sensing, what is very important for us and for EPS is that we do not need skin preparation. We do not need to put a gel to improve the contact between the skin and the electrode. And there is no risk for allergies, and there is no risk for skin irritation. So this is really well suited for a very simple, convenient deployment of the electrode on the users. So besides physiological sensing, there are a couple of other applications that are brewing in the lab. We're looking at measurement of stress in rocks and concrete. This is a collaboration with the British Geological Survey. We're looking at measuring the blade clearance in gas turbines. This is a collaboration with Megit Sensing Systems and Plessey Semiconductors. And the technology is also scalable. We can make it larger or smaller in terms of electrode size. And if we miniaturize the electrode down to the micrometer level, this means that we can create an imaging array. And we have shown that we can actually use this imaging array to measure the charges that are deposited on a surface. For example, after touching the surface, we can use it to pick up the fingerprint of the user. As the charges are diffusing over time, we can also estimate how long ago the fingerprint was deposited on the surface. My group is interested in wearable technologies. I am interested in creating wearable smart assistants that are able to understand the user need and provide information or assistance in real time without even the user having to ask for help. This, of course, requires to understand the user needs, and therefore my research is focusing on the automatic recognition of human activities and the context in which they occur. For example, we are interested in recognizing gestures, such as drinking from a glass, or maybe opening a door, closing a door, opening a drawer. We are also interested in higher level activities, such as detecting a breakfast or a meal, or looking at the daily routine and analyzing these daily routines to understand that one day was more stressful than some other day, then one day was a working day, and another day was a leisure day. We're also interested in recognizing social interactions between people and cognitive and affective states. This is all supported by wearable sensing, so sensing on the body, and on-body processing. In this way, we have a complete self-contained solution where both sensing and processing happens on the body without the need to send any data outside. So this is advantages in terms of privacy preservation. So a system that is activity and context aware should be able to answer a question such as, what did I do yesterday? And we would like the system to be able to answer that, well, yesterday I maybe was at the supermarket. So the system should be aware of my location. It should also be able to understand that yesterday I was there for a coffee and not for shopping. So it is able to analyze my movements to understand that I went to the supermarket to take a coffee. It can possibly also understand that I took a coffee with a friend called Lisa based on speech patterns, and that I actually enjoyed taking this coffee by some form of emotion recognition. If I would be asking the question, what am I doing in the kitchen now? Based on my past history, my habits, my just preceding gestures, the system should be able to detect that possibly this day I was about to cook some spaghettis. So this kind of very detailed recognition of activities has a lot of potential for healthcare applications, in particular for people that suffer from memory loss or dementia. We can think of creating a textual life log of their activities, a textual diary that is created automatically from sensor data. And this can help relieve the stress of facing missing memories. In the same way, we can actually provide hints or information about activities that should be performed and that were forgotten. So again, this is something that can improve the quality of life of people that suffer from dementia. We can also support desired behavior change, for example, to fight obesity, by inserting in daily life very, very specific cues at precise moments. For example, if somebody is about to hesitate between taking the staircase or taking the lift, the system could provide a hint suggesting to take the staircase, but only if the user is going to be willing to take this hint. So the system must have a very good understanding of the current context of the user. This kind of insertion of cues in everyday life can also be used to support people facing depression, and it could also be used to better manage spending or maybe reduce energy usage. Activity recognition can also be used in the industrial setting, of course to increase safety, but what we have in mind for the long term would be teams of robots and humans that are collaborating in a manufacturing process and that can seamlessly interact thanks to activity recognition techniques. Of course, for this technology to be accepted by users, the sensors must be made invisible or as small as possible. Here on the left, you can see one of the miniaturized sensor platforms that we have developed. It is smaller than the size of a conventional watch. And this platform developed here at the University of Sussex can measure movement, height above ground. It can pick up sound. It can measure temperature. It can measure light. All the processing can be done on the device itself. Data can be also stored here, and the system can communicate with a mobile phone. If we miniaturize that further, we can also include sensors into jewelry, into other kind of accessories such as bracelet or maybe shoes, and maybe even the clothing and the button of a shirt. So the sensor commonly used for activity recognition is the acceleration sensor. It's a kind of motion sensor. You can see here this sensor that is being dynamically moved, and in the waveforms you can see that it is able to pick up this dynamic motion forward, backward, laterally, and vertically. Acceleration sensors can also pick the orientation. For example, here when the sensor is moving very slowly, we can see in blue and red here that we can measure the orientation of the sensor with respect to the ground. So if such a sensor is placed on the body at one or several locations, then we can get a good understanding of the orientation of the body, but also of the movement and the gesture of the person. So one big domain for wearable activity sensing is in the sports domain. For example, to collect statistics about a game and provide information to yourself and your friends, but also to analyze precisely the movement of a player as a way to improve the technique. So what we have done recently here at the University of Sussex is measuring the movement of players of beach volleyball. We collected the data from sensors placed on the hand, on the lower arm and the upper arm, sampled at a very high rate, and we observed players during training and during actual games as a way to understand whether we can improve the technique of the player, in particular during the serve. You can see here in the video the player that is about to perform a serve, and you will see that when he's hitting the ball, there is a very characteristic signal pattern which is arising. And the signal pattern is very unique to the serve. It doesn't occur in other parts of the gameplay. So this makes it actually very well suited to be picked up by an algorithm specifically trained to recognize this serve. And of course, in the future, we can look also more precisely at the exact nature of the signal to find a way to improve the serve style of this player. So in order to recognize the activity of the player and spot this serve, we need to develop algorithms to recognize activities. So this usually combines the data of multiple sensors with sensor fusion techniques, and these sensors can also be multimodal. So we can combine motion sensors together with sensors of, let's say, sound or altitude. This usually provides a more precise recognition of activities. So when we design a recognition system, we combine elements from signal processing, machine learning, reasoning, and depending on the application requirements, we either focus on high performance, on low power usage, or on low latency. We have recently introduced a method that is able to spot patterns in continuous data streams. It is a template matching approach that is very, very well suited for low-power platforms. We showed that it was possible to detect a serve automatically and with high accuracy using only 135 microwatt of power. This is a very low power consumption, which is very well suited for wearable systems. Obviously, this technique can also be used for other kind of activities besides detecting serves, such as detecting whether somebody is opening a door or opening a drawer. Another domain where activity recognition is very important is in the field of healthcare. Here we have looked at one of the issues that is commonly faced by people that have Parkinson's, which is a gait anomaly called freezing of gait. So when the person is walking, it can happen that suddenly he or she stops walking and is unable to pursue walking and appears frozen on the ground. This is a situation where the person is conscious of the issue, but is unable to pursue walking during a couple of seconds or up to tens of seconds. So what we have done is deploying the same kind of sensors on the body of a person with Parkinson's disease. And we have collected the data while the person is walking normally or while the person is experiencing a freeze. And you can see that the sensor signal look very different in the case of normal walk, here in green, or in the case of freeze, here in red. This allows us to develop algorithms to automatically detect the freezing of gait, and then we can use this to trigger an assistive cue. This work was first introduced by us, and now it has been continued by many other groups. Some of the groups are looking at some preliminary clinical trials to see if this combination of automatic recognition together with assistive cues is actually beneficial to the patient. In wearable computing, it is very important to be able to integrate the sensors as close as possible to the body, possibly even in textiles. And flexible electronics is a new direction in electronics research, where the idea is to create electronic substrate on plastic foils that can be bent and integrated around any kind of everyday object. The flexible electronics research group is looking at high-performance electronics on plastic substrates, and in particular, it uses oxides instead of organic material because of the better electric properties. You can see here on the left the fabrication of an electronic circuit on a freestanding plastic foil. This is a polyimide. And here we can see the different layers making a bottom gate thin film transistor. So the steps required to produce this structure are exactly the same as the ones used in traditional semiconductor manufacturing processes, such as photolithography, material evaporation, or etching. Now, by combining multiple of these sensors on a larger foil, we can build more complex circuits. Here you see an operational amplifier made of many transistors that can be used as an amplification stage in a sensor. So building sensors on a flexible foil has a lot of interesting advantage. If you look at this plastic foil here, it has a weight of only 2.5 grams per square meter, and this is less than 1/10 of the weight of a sheet of paper. So this is interesting because it contains all the electronics within this very, very limited weight. Also, the foil can be transparent. It can be manufactured on a very large scale and can be manufactured at low cost. Finally, this structure is bendable. Here you can see the plastic foil that has been wrapped around the seed of a dandelion. The electronic structure is entirely functional, and the mechanical properties of the seed are not affected. And actually, we can bend this structure down to a radius of 50 micron, which is about the size of a human hair. Here you can see the foil being wrapped around a yarn that has been then woven into a textile, and this makes it very useful for smart garments that can measure physiological parameters or that are able to measure movement of the person, for example, in wearable computing applications. Finally, the next steps beyond flexibility consist in creating stretchable electronics, for example, following this kind of accordion structure. And current results show that you can reach a stretchability of 200%, which is more than the stretchability of the skin. So this is a very important step to build a flexible, stretchable skin that could be applied in robotics domain, for prosthesis, or for biocompatible electronic implants. Of course, with all these sensors that are available, we need to interconnect them as a way to get the information from one sensor to the other and to get the information to a central place to analyze the data. There are many new and emerging requirements given by a plethora of new applications in wearable sensing, but also in vehicular technologies that require new communication technologies. And the Communications Research Group is addressing many of these challenges, focusing on specific areas where there are very important needs. For example, one main area of research is 5G mobile communications. This is the communication protocol that is going to be used after the current generation 4G protocol that we currently find in our phones. And the research here is motivated by many new application scenarios that arise in the last many years. For example, we want devices that communicate to each other. Vehicles have to communicate with each other as well on motorways to improve safety. Machines have to communicate with each other in industrial plants. In some cases, we have devices that move at very high speed. In other cases, we have an extremely high density of devices in a limited geographical area. For example, if you think of a large-scale social event in a city, a mass gathering, you have an extremely high density of people that all want to have access to fast data. In many applications, such as wearable computing, but also environmental monitoring, we're dealing with systems that are operating on batteries. Therefore, we rather want to have very low power communication. But in other cases, we want to have very high bandwidth, for example, to transfer multimedia data. So all these requirements are somehow conflicting, and the research group is looking at how to merge and combine these requirements with technologies that are adaptive and can address and fulfill these different requirements at different points in time. Here you can see one of the test bed of the Communication Research Group, which is looking at communication in mobile and wireless sensor networks. These units here are partly autonomous, and they could be, for example, sent to a planet such as Mars, where there is no global communication infrastructure. But they nevertheless need to communicate data between each other. Given that they may be out of communication range directly, they need to relay messages between each other. Therefore, one of the main challenges that the group aims to address is communication between moving sensor nodes and looking at optimal routing protocols that allow to deliver data with minimal loss or with minimal latency. Ultra-wideband is commonly used for high-speed communication, but it is also interesting for applications in biomedicine. For example, it can penetrate through the skin, but it is also a non-ionizing radiation. So the group has developed an imaging technology based on ultra-wideband that is able to detect breast cancer with much better results than competing technologies, and especially also with higher resistance to artifacts. This basically means that the same technology, ultra-wideband, can be used both for communication but also for imaging or sensing purposes. Finally, as the number of sensors become larger, there are new sensor data applications that become possible. Here you can see a setup where an environmental station has been deployed in multiple areas in the city using a low-power communication protocol developed by the group here at Sussex. And as the number of this kind of station is deployed, as the number of this station is increasingly deployed, we can start to get a picture of the pollution in a city. This allows to do some data-driven infrastructure planning, such as understanding where to put green areas in a city or where to put or how to reshape traffic patterns as a way to minimize pollution. Here on the right, you can see a mobile application that is installed in the dashboard of a car. This application is analyzing the movement patterns of the driver, but it is also looking at the movement of the car, and it aims at improving the driver comfort by providing suggestions for music. And these suggestions are partly coming from the analysis of the driver, but also from recommendations from similar drivers that are using the same system. So here we have the capability to analyze on a large scale the behavior of different drivers, understand their movement patterns, and as a benefit to the users, we can provide them a service which is decreasing their stress in daily commute. The last group in our center is the Semiconductor Materials and Device Laboratory that has been founded by Dr. Anna Barnett in September 2013. Currently, the group has 4 PhD students, 2 postdocs, and it is looking mostly at semiconductor materials that are other than silicon. This means 3-5s, silicon carbide, and diamond. The main objective of the laboratory is to develop detectors and instrumentation for photon counting spectroscopy at X-ray and gamma ray energies. It also does beta spectroscopy and UV detection. The group is also developing all the ultra-low power electronics which is required to support this kind of sensors. As a main application, the group is looking at instrumentation in extreme environments, in particular currently for ocean mining. The sensors that are developed by the group with these new materials allow to create detectors that operate at much higher temperature compared to traditional silicon. For example, up to 130 degrees Celsius, whereas silicon can only operate at -30 degrees Celsius. So this provides an advantage and leads to smaller sensors and cheaper sensors. These sensors can also be placed in environments where it would not be possible to place silicon. In particular, these detectors are radiation hard, so they can resist intense radiation where actually silicon would be damaged. This means that we can place these detectors in very interesting environments, for example in space, but also on Earth in a nuclear reactor. One of the challenges in electronic systems is to obtain energy at a low weight and for a long period of time. And one of the spin-off the technologies of the group is a new class of Betavoltaic power sources. Those are similar in principle to a photovoltaic source that converts light into electricity, but in this case it converts a photon into it converts a beta particle coming from a beta-emitting radioisotope into electricity. This can be made in a safe way and can operate for decades. So this long operation, up to decades, is actually very, very interesting if you cannot or if it is not convenient to replace the power source, especially in the case of implants. It is also interesting if you want to power embedded systems where the environment is too harsh for traditional chemical batteries, for example in space. So this concludes our introduction to the different groups in the Sensor Technology Research Center. I would invite you to look at our website for more information, and thank you for listening.